Hello everyone, my name is Yifan. Today I'm going to talk about how to do regrasping with a simple gripper. This is joint work with Zheng Zhongjia, Aaron Johnson, and Matt Mason. So robots do a lot of object manipulation in modern factories, and more often than not, they need to change the grasp orientation of the object. But industrial robots usually do not use very dexterous hand, so they have to do it by put down the object on some fixture, move the robot, then grasp again, which is simply too slow compared with human. Human would take a more direct approach, that is, in-hand regrasp using finger and wrist rotation without breaking contact. People do this every day when you pull your phone out of your pocket. So we want to make a robot, let the robot to perform this maneuver. So we build a robot to imitate this human motion. Similar with human, the robot uses wrist rotation to generate inertial force, use gripping to generate frictional torque on the object, use these two forces as extrinsic actuation on the object. Before we talk about how this works, let's look at some related work. The idea of using inertial force is not new. Actually, if we treat the contact as a perfect pin joint without friction, then the problem essentially becomes a passive last joint manipulator, which is rarely solved in control community. One popular approach is the so-called partial feedback linearization, in which you linearize and do control on one degree of freedom, then try to prove the other degree of freedom is also stable. However, in our pivoting problem, friction is far from negligible. In that case, the original provement of stability doesn't hold anymore because the problem is non-smooth. There are some works that does consider friction. She tries to solve not just pivoting, but the full planar regressive problem, including both rotation and translation. He used inertial force to move the object really quickly. However, the overall convergence of the method is quite slow and takes several iterations. We believe that's partly because he's not doing closed-loop control, and there are lots of uncertainties at the contact. So what uncertainties? Firstly, friction. There is no perfect friction model. Any practical friction model has to live with uncertainties. Also, as long as you are not putting markers on the object, then the robot might not have a perfect knowledge of where is the object, because the initial grasp position might not be exact, and there could be some slip during the motion. So we believe the solution is to close the loop and add grip force as an additional source of control so that we can have more control authority on the system. Speaking of gripping force control, recently there are some works using grip force to do pivoting under gravity. Their work shows that grip force is indeed useful for this task. However, if you use gravity, then you cannot recover from overshoot, so the method is kind of prone to disturbance. So it seems that if we can use inertial force and grip force together, then we're done, we solve the problem. However, that turns out to be quite challenging. Because if we use them together, as we have saw in the video, the pivoting direction will change quite often. And if that happens, at the switching point, the Coulomb friction model is discontinuous, and the stiction is non-smooth. So the problem becomes non-smooth. A more subtle problem is that if there is no gravity as offset, then we observe that the controller will often produce a negative grip force. So the problem is not solved. And what we're going to present today is a controller design that uses both inertial force and grip force to do dynamic pivoting. And we handle all the aforementioned issues, including the model discontinuities and the positive lower bound constraint on the input. And we do closed-loop control to obtain fast convergence and being robust to uncertainties and disturbance. Let's firstly clarify our assumptions. So we assume that we know the dimensional and inertial property of both the object and the robot. We assume all the motion happens in the horizontal plane, so we are not considering gravity. And we assume the object will not slip off the gripper. So it can slip, but will not slip off. So under the last assumption, we can still model the contact as a pin joint, whose joint torque is given by the contact friction. And then we can use the angle alpha and theta as state variable, use torque and grip force as control, and write down the system dynamics. Note that the inertial property of this new last link is uncertain because the grab position has uncertainty. Okay, for friction, the choice of friction modeling is always a trade-off between accuracy and simplicity. The one that works well for us is the Coulomb friction plus stiction, which gives us a hybrid system with 5 different modes. Each mode has its own continuous dynamics. Okay, so now let's firstly design a controller that works for one mode. Within one mode, we have a continuous system that is nonlinear and has bounded uncertainty. There are a ton of methods to cope with this kind of system, and the one we tried is the sliding mode control, in which we basically use a controller that's parameterized by a GAN vector k, and the worst case convergence guarantee is provided by the so-called sliding condition, which can be formulated as a affine constraint on k. So usually we just solve a feasible case and we are done. However, it turns out that doesn't work because we observe that the number of force calculated by this sliding mode control is often a large negative number, which is not realistic. So what if we just apply the saturation constraints? Well, if our estimation of uncertainty bound is not very tight, then the sliding condition becomes so conservative that we just have no solution. So how can we cope with that? Notice that we don't need decay here to be super big. Equality is all we need. So we can instead just apply the equality constraint by minimizing this. We apply it by soft constraint by minimizing this cost function and satisfy subject to the saturation constraint. The second term is basically regularization. The idea here is, well, we have to satisfy the saturation constraint, but for the sliding condition, we do what we can. The problem turns out to be a quadratic programming, so it can be solved very efficiently and always have a solution. Okay, we have solved the problem for one mode, but remember the problem has 5 different modes. If theta dot is not 0, then we basically just solve the corresponding mode. But if theta dot is 0, then we'll face the ambiguity of 3 possible modes for next time step. So we use the idea from hybrid control theory. We basically solve each mode separately with their condition as additional constraint to make sure the solution stay within that mode. The problem turns out to be still a QP. And after that, we just pick the solution that gives us the best cost value. Okay, now how does that work? So we compare our method with 2 baselines that do not use grip force control. The first one is the partial feedback linearization. That method works fine in our simulation if there is no friction. But as soon as we add friction, the method failed in both simulation and experiment. The second baseline is our hybrid control, but only using grip force. Okay, so in the first experiment, we evaluate how many consecutive pivots we can do before divergence. This is challenging because all kinds of error will accumulate with time. PFL failed immediately, and hybrid control with inertial force got 1 success, and our 4 method can at least do 4 pivoting consecutively. That's not written. Okay, in the second experiment, we evaluate the robustness of this method to the grasp position uncertainty. We basically run the experiment multiple times with different initial grasping position unknown to the object. The initial grasp position is shown in the right figure as the dots. The outside square is the size of the object. The task is to pivot the object to 1 rad within 4 seconds. There are 3 possible outcomes. A green dot means the motion converges to the goal within 4 seconds. Blue dot means it's converging but did not stop, and green dot means it converged. And clearly, our method converges quickly and has the largest contraction region. Okay, so this is a typical state trajectory of our 4 method. We can see that the pivoting angle converges to the goal, and while the wrist rotation is confined within a relatively small region. The right figure shows our low-level grip force controller. Actually, it looks like it's quite noisy, but our system stability can still benefit a lot from that. We also did some qualitative comparison on disturbance rejection. The result is quite obvious. PFL failed as expected, and our 4 method can handle the largest disturbance. So conclusion is, for dynamic pivoting, it can be more robust if we use both inertia and grip force with our proposed controller. And grip force is very useful even if it is noisy. So Dr. Landry, apparently we did no learning or any online adaptation in this work. So we are currently working on incorporating learning methods so that we can adapt to different objects online. And sadly, we don't have a formal guarantee on worst case convergence because we have so many constraints. So unless we have a tight estimation on the uncertainty bound, we will not have a feasible guarantee. And also, the current hardware has a bunch of limitations, and we are currently building a parallel gripper that supports very high bandwidth force control, so that we can have better performance and test some new ideas. This work is supported by NSF. Thank you.
First question from Matei.
All right, thank you. So first of all, I think it's great that you're looking at this kind of complex manipulation tasks. Love to see us go beyond quasi-static. My question is, I think one of the most interesting things to me about the work is that you don't know what state you're in. Are you sticking, or are you about to slip, and in which direction? And you are able to be robust to that uncertainty. You solve for all possibilities, and then you go forward. But what happens if you're wrong, right? If you choose the one with the lowest cost, but that's not the state you're in. You assume you're sticking, for example, but in fact it turns out you're just starting to slip. So you're solving for the wrong mode. What happens next? How come that you're still robust to that it still works out in the end?
Yeah, thanks. That's a very good question. Actually, in our case, if we face the ambiguity of multiple modes, in our model, our control vector can determine which mode we will be in. So if we are solving for one mode, we will add constraint on the control to make sure that mode will happen. But what if we are still wrong? What if our model is incorrect and we end up with some different mode? It turns out the mode transition is mostly happen between the right sliding and left sliding mode. And but for the ambiguous mode does not happen very often. They happen more often only towards the end of the convergence, and thus it will cause less problem. But that is definitely something we can consider in the future work. Like if we have, how do we have a better sensing and detection of the mode? Thank you.
Could you tell me why Could you tell me why the gripping force could be negative? I didn't really understand that.
It cannot be negative. So in the model, if we do not add this constraint, the controller will sometimes think, well, it will be good to have a negative grip force, because if we just look at the mathematical model, that's basically a linear. The grip force, the friction is basically is proportional to the grip force. So the controller really doesn't know why it cannot just go negative. So if it thinks a negative friction is useful, the controller will generate a negative grip force. But in reality, that we cannot command such control. So we need to, from software, constrain this situation.
Is that like a Pan-LaVey type configuration?
Sorry, I don't understand.
Is it a Pan-LaVey paradox type? I'm still not seeing exactly how the normal force, the predicted normal force, could be negative.
Why it cannot?
It's compressive.
Yeah, we can discuss later. Maybe we can. Yeah. Thank you.
Okay. Thank you.